essentially in a consistent and complete manner. The static analysis tools bring their knowledge along with them. They make it possible for non-experts to contribute to a security code review process. Finally, the static analysis tools are useful for all kinds of code, not just web applications. They're not nearly so reliant on what sort of protocol the code is speaking. All right. Before you get too excited, I have to say that static analysis is not perfect. You can't find all kinds of defects this way. And let me give you a couple reasons why. Static analysis tools don't understand the architecture of your code. And that means they can't tell you what the most important place you're receiving input from, or what the most important and critical operation is in the code. You have to bring that knowledge to an analysis of the static analysis results. The static analysis tool doesn't by itself understand the semantics of your application, which means it doesn't know what critical operations look like. And lastly, it doesn't understand the social context in which your application runs. Some vulnerabilities aren't even vulnerabilities if they appear in the right kind of application. You have to bring that analysis along with you in order to interpret the static analysis results. Here's a nice thing about static analysis, or any analysis tool really for that matter. There are really only two mistakes you can make. You can either report a bug when there is no bug, or you can fail to report a bug when there is a bug. False positive means you pointed out something and it didn't really matter. They result from the static analysis tool having an incomplete or an inaccurate model of the code, or performing a conservative analysis. In other words, it would rather err on the side of caution and tell you about an issue and let you decide whether it's important or not. Static analysis tools generally generate false negatives too, so they miss some bugs. They can miss bugs for the same reasons they report things that aren't true, and that is their model of the code might be off. They might be missing rules that tell what's a bug or what's not a bug, or they may perform some sort of forgiving analysis where they say, that's really not going to go wrong. Okay, so now I'm going to talk a little bit about what makes static analysis tools tick. Essentially, you've got to take the source code, turn it into a model of the program, then apply analysis techniques, one or more analysis techniques, and then finally hand off your results to a results viewer. So, people often focus on the algorithm as being the key component of a static analysis tool, but I want to talk about a couple of other things that are key components. The second one on this list is language support. You know, that one is so obvious, I think sometimes it just gets overlooked. Capacity is important because you want to be able to make sure you can analyze your whole program at once. The rule set that you use to analyze the code is critically important because it tells the analyzer the difference between good code and bad code. Finally, results management, including prioritizing the issues. We already talked about that one. Controlling what to check for. If you have a bunch of rules, but you know that they don't all apply in one context or another, you might want to narrow that down. And finally, if you do have to look at a false positive, you'd like to not ever have to look at it again. Okay, just a few words on analysis techniques. I'm going to give an example here of doing static analysis for taint propagation. The idea is we've got some input that comes off of a network and goes into a buffer. We copy that buffer around through the program, and then at some point call exec on it. I'll call that a command injection vulnerability. What the static analysis tool does is it traces the potential path of execution through the code and points out where input enters the code and where that could be used against the program. Of course, this is a very short example. The sorts of things we've seen Sean have on his screen have crossed method boundaries. Parsing, language support is at the top of that list. Supporting one language or compiler, that's maybe not an easy task, but it's at least a straightforward one. Supporting a lot of languages and compiler combinations is tough. Analyzing compiled code is one potential way you might get around that. In other words, who cares what the compiler does? Let me just take the binary and look at that. After all, everybody's got it, and you don't have to guess at how the compiler is going to transform that stuff, and you don't even need rules to tell you about how to model the behavior of the compiler. There are a few problems with looking at the binary, too. First of all, decompilation is difficult. It's not so difficult for Sean today if he'd chosen to go that route, because he would be looking at Java bytecode. That's pretty easy to reverse. If you look at native executables, though, that decompilation problem becomes a lot harder. The loss of context that you get from looking at compiled code can hurt a lot too. If you think about what a JDBC driver looks like once you've compiled it, it looks like take some stuff, put it on the network, get it back from the network, hand it off again. You can't tell that there is potentially SQL injection in there. Lastly, even if you look at the compiled code, you still need the source because there's no way you're going to fix the bug unless you can find it in the source code. Next, I want to talk about scope versus performance. I talked about doing taint propagation. There are taint propagation and related techniques generally take more time and act better if you give them more of the program to look at. So along the bottom axis, I talk about analysis scope. Those early tools like RATS and ITS4 were really looking at one line at a time. Tools that are more sophisticated, like the one built into Visual Studio, MS/Analyze, looks at more like a function or maybe a module at a time. The static analysis tools that are generally aimed at security these days look at a whole program or maybe even a little bit more of a program, but generally speaking, they're not going to run in the blink of an eye. Now I want to talk just a little bit about rules. So I'll talk about one type of rule being structural analysis, and this is essentially equivalent to what those old-fashioned RATS ITS4 flaw finder tools would do. I've got an example implementation of a structural rule that just flags a call to getS. And that's really all you need if somebody calls getS. That's a security vulnerability right there. You don't need fancy analysis in order to catch that. I'll put a more sophisticated structural rule up on the screen next. The idea is if you call realloc on a buffer and assign the result into that same buffer, if the call to realloc fails, then you may have just leaked that memory. And there's a structural rule up on the screen that describes how you can explain that property to the analysis engine.
Brian, I want to interrupt for a second. We actually have a new entry into the competition. Eddie is pulling up a proxy tool to do a little manual fuzzing, it looks like.
Hey, can we put the results on the left on the screen, or is that hard? I'm sorry, on your left, Jacob, all the way over. Because I see Eddie got results out of the testing tool.
We can try. You can keep talking.
I don't want. Okay. He's got some
Those
up
are
there.
the same results.
So he's in Visual.
Both tools are telling me about the same thing right now. It looks like.
He was in Visual Studio. He's still in Visual Studio, and the tool is still running. Is the way it looks to me.
Only 48% finished, and he's about halfway through his time.
Mm-hmm. All right. Next up, we're going to talk about analysis rules and look again at that data flow or taint propagation example from earlier. So the idea is we're going to follow values through the program, but what kind of rules do you need in order to do that? The first thing you need is a source rule that tells you get input from network means an attacker might be able to control that value. The function get input from network is the one we're talking about, and we'll establish a post condition that says the return value from the network is tainted. The next thing we need is to look at that, the analysis engine, take that buffer and watch that it makes its way onto the next line. Then we'll define a pass-through rule. The pass-through rule basically wants to explain what copy buffer does. It takes the contents of the buffer on the right and puts it into the buffer on the left. So that's a rule for the function copy buffer with another post condition. That post condition is the second argument is tainted, and then if the second argument is tainted, that means that the first argument becomes tainted. Generally speaking, in order to do a good job of analyzing this code base, my guess is the static source code analysis tool had to apply thousands of these rules. Finally, we'll take a look at a data flow sync rule. This is basically the money shot. This is where we say if you see a call to exec and a precondition for exec is, if you see tainted data make its way to exec, that means you've got a vulnerability. All right. The final point I want to make about the static analysis tools is about the interface. The interface is probably the most ignored critical aspect of a static analysis tool because it's the part that's got to convince a programmer that there's a bug in their code. Generally speaking, programmers aren't looking for some sort of little robot piece of software to come out and tell them what they're doing wrong. So you also have to apply this interface in more than one scenario. Consider a case where a security auditor is parachuted in and needs to take a look at 2 million lines of code, or maybe just 128K worth of code, but in a really compressed time span. They want one interface, whereas a programmer who's doing a desk check of their own code probably wants a different take on that same data. A third interface you might want for supporting a collaborative sort of code review scenario. I'd say that the interface is just as important as the analysis techniques that you apply, because if you can't convince somebody to change their program, then it doesn't matter whether you've done any analysis or not. Lastly, that interface is where you want to show, where you want to make sure that somebody doesn't have to look at the same bogus result more than once. So you need some kind of suppression system to make sure that they stay on track.
Okay, time check for the chefs. You guys have 15 minutes left.
15 minutes total, or 15 minutes to look at the code? 15 minutes before presentations begin?
Exactly.
All right. So, last point on this slide. If you'd like to take a look at a static analysis interface, please go check out the Java Open Review project. Essentially what we do is we pull in open source projects and we analyze them using Sean's static analysis tool, and then we shoot those results back to the people who made that code. We've got a couple of sample projects online. One of them's for the OWASP WebGoat project, which, glory be, has security vulnerabilities in it. And so you can kind of get a hang of what this interface looks like. You can Google Java Open Review or go to opensource.fortify.com. Lastly, I don't know if we've caught Sean with this on his screen yet or not. So I sort of showed what data flow looks like through the code, but hopefully we'll see here in a couple minutes that he's using an analysis trace feature built into the GUI tool that basically gives him a very UML-like breakdown of what that path through the code is. You can see that, let's see, all the way over on the right-hand side of the screen is where the tainted data enters the program, but that's 3 levels down deep into the call stack already. So that tainted data actually makes its way back up the call stack before it makes its way to the sync node all the way over on the left-hand side of the screen. All right, that's the end of the static analysis talk. Can we flip back over and see what Sean's looking at now?
How about Jeff?
Yeah, show him part of the screen.
They decided to go back to their real resolutions as opposed to the little small one that the projector can handle, and now they're worried that it's going to blow up. Let's see what happens. Maybe we'll get a little bit.
You're going to take down my machine.
Oh, Sean thinks I'm sabotaging him now. He said I crashed his computer by changing the switch next to him. All right, Tosha, you have a time advantage now. Sean's machine is completely frozen. Go for it.
What else could we use to handicap these guys at this point?
We could switch to Jeff's machine, too. Maybe it'll have the same effect. So we're on an error page. I'm sure there aren't any cross-site scripting vulnerabilities there. You don't have time to make a new logo. Oh, he's thinking about presentation material.
So how do we handicap these guys at this point in the presentation? Can we switch to Toshi's monitor?
Nothing interesting.
But there are more stack traces. I like those. Which one?
So Toshi seems to have gotten results out of the client or the server side instrumentation, and so he's looking at a stack trace that he